Hello everybody. Just a huge well done. I am so impressed with the effort that the majority of you year 10s are putting into your work at the moment, and I have no doubt that in time it will most certainly pay off. I just thought I'd give you a bit of feedback from the quiz results, and there were one or two questions that tripped a few people up, and I know we learn best from our mistakes, so I just wanted to help you through them. So let's have a look at the questions that you had to go through last week. So the first question, peer theory. It's what we learned. We learned that breaking bonds, I've got to put in energy to break that bonds. Making bonds releases energy. Now, one or two of you put produces energy, and if you remember, never, 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 never say produces energy, because that gives the idea that it just suddenly came out of nowhere. And we know from the conservation of energy that it's always there. It just changes from one form to another. And both in chemistry and in biology exams, the examiners are told to be very, very strict about this. So it is releases rather than produces. And bond energy is the average energy to make or break a bond. You did very well with that. And then this little graph over here. Now, from this graph, we can see we've got the reactants above the product. So we're getting that Z shape. So straight away, X, Y, Z, exothermic gives us the Z shape graph. Okay, hopefully you guys can all pick that up very, very well. And then we had this graph. Now straight away, without even knowing what the question is going to ask, because the product's energy is higher than that of the reactants, and I have an S-shaped graph, it's got to be the opposite. This is going to be an endothermic reaction. Now, this question, which statement about this reaction shown in the graph is not true? Now, before I even look, let me just spend a bit of time looking at the graph. From the graph, I can see the energy of the reactants is above the energy of the product. So I get this Z shape. So I know that I am dealing with an exothermic reaction. Can you see how I'm taking time to study the graph? Because they put it on there for a reason, not to make the page just look pretty. So it's an exothermic reaction. Yes, it is, because X, Y, Z. It's a Z-shaped graph, which is exothermic. The overall change in energy is negative. Yes, we know in exothermic, it's a negative change in energy. And if we go products minus reactants, it's going to give us a negative number. So, for example, 2 minus 5, we're going to get a negative number. The energy released in making the bonds is greater than breaking the bonds. Yes, because there's a lot more energy involved in going from there to the bottom. So the overall change in energy, yes, that's quite true. The overall change in energy is positive. It's not, because that would be for an endothermic reaction. If you're having problems with that, please just email me. Okay, now some of you don't love this as much as you could. So how many carbon-hydrogen bonds? Now, to look for this, every time you've got a carbon and a hydrogen, you've got that line. Imagine it like a little child being very, very naughty and pulling the little legs off their favorite toy. Okay, maybe they've got an octopus or something like that. Imagine you were pulling off each one of these little bonds here. How many would you have in total? So we're not counting the ones between carbon and carbon. Remember, the bonds are represented by these lines, and because it's a single line, it's a single covalent bond. So, carbon, hydrogen, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So, there we have our answer. Okay, the unit for bond energy is kilojoules per mole. And of course, I was using fruit pastels, and this was my little test to see if you were in fact not cheating and just skipping through to the quiz. Not that you would ever do anything like that, of course. But this question really separated a few of you. So let's have a look. You can do this. Hydrogen bromide decomposes to form, decomposes means it breaks down, and in a decomposition reaction, I've got one reactant forming two products. So it forms hydrogen and bromine, and they show you what the bonds look like in it. They say you've got two hydrogen bromide particles. Use the table to calculate the energy change for this reaction. Okay, so let me show you how you had to work this out. To calculate the energy in, we know from the table that HBr has an energy of 366, and you needed to go 2 times 366 to give you that answer of 732 kilojoules per mole. And because it's energy in, that is positive. Energy out is 436, because I've only got one HH bond, and the value for BR bond from the table was 193. That gives me a total of 629, which I can always double check on my calculator. The change in energy is the energy in minus the energy out. So I'm going to go 732 minus the energy out was negative, so minus 629, giving me an overall answer of plus 103. Now remember, it was really important to, and there were two choices, positive or negative, because the energy in is greater than the energy going out, I'm going to get a positive answer. I hope that helps. If you need more practice, I can send you more examples.